Understanding algorithm efficiency through time complexity analysis. In the world of computer science, algorithms are the backbone of problem-solving in software development. As programmers, we often find ourselves choosing between different solutions to implement our logic. The efficiency of an algorithm determines how well it performs under varying input sizes. This brings us to the critical concept of time complexity analysis, which helps evaluate algorithm performance objectively. What is algorithm analysis? Algorithm analysis involves evaluating the performance characteristics of algorithms before implementing them. It focuses on understanding how an algorithm behaves as the size of its input grows. This process allows developers to make informed decisions when selecting algorithms for their projects. Instead of relying solely on empirical testing, theoretical analysis provides predictable results that remain consistent across different environments. There are two primary aspects to analyze in any algorithm. Time complexity measures how much time an algorithm takes relative to the input size. Space complexity evaluates the amount of memory required by an algorithm during execution. By analyzing these factors, developers can identify potential bottlenecks early in the design phase. This proactive approach leads to better system performance and resource management. For example, consider sorting algorithms where bubble sort has O(n) superscript 2 time complexity while merge sort offers O(n) log n. The choice between them significantly impacts application performance at scale. Why time complexity matters? Time complexity serves as a crucial metric for comparing algorithms. It quantifies how the runtime increases with larger inputs, allowing developers to predict performance trends accurately. When working with big data sets, even small differences in time complexity can lead to massive variations in actual processing times. A linear time algorithm will outperform a quadratic time solution dramatically as input sizes grow. Let's take a practical scenario: searching through a database containing millions of records. An efficient search algorithm could reduce query response times from minutes to milliseconds, making applications feel faster and more responsive. However, it's essential not to over-optimize too early in the development cycle. Sometimes, simpler algorithms with slightly worse time complexity may be preferable due to easier implementation or maintenance benefits. Introducing Big O notation. Big O notation is the standard way to express time complexity in algorithm analysis. It describes the upper bound of an algorithm's running time as the input size approaches infinity. This asymptotic notation abstracts away constant factors and lower-order terms, focusing only on dominant growth rates. For instance, O(n plus 100) simplifies to O(n). Because constants become insignificant for large values of n, developers use Big O to classify algorithms based on scalability. Common complexity classes include O(1), O log n, O(n), O(n log n, and O(n superscript 2). Understanding these classifications helps in making educated choices about which algorithms to implement for given problems. It also enables communication among developers regarding expected performance characteristics. It's worth noting that Big O doesn't measure exact execution times, but rather the rate at which runtime increases with input size. This makes it particularly useful for comparing algorithms theoretically. Analyzing common algorithms to understand algorithm analysis better, let's examine some common algorithms and their corresponding complexities. These examples illustrate how different implementations affect performance. Consider array access operations. Accessing elements in an array typically requires O(1) time since any element can be reached directly using its index. On the other hand, inserting elements into arrays usually takes O(n) time in worst-case scenarios. This happens when adding items to the beginning of an array, requiring shifting of existing elements. Searching through unsorted arrays necessitates checking each element until the target is found. In such cases, the average case becomes O(n), while the best case remains O(1). Solving problems like finding duplicates in an array introduces interesting complexity trade-offs. One approach might involve nested loops leading to O, n superscript 2 complexity, while another method utilizing hash tables reduces it to O, n. These comparisons highlight why careful selection of data structures and algorithms is vital for optimal performance. Choosing the right implementation can drastically impact application behavior at scale. Practical examples of time complexity real-world applications provide excellent contexts for examining algorithmic efficiencies. Consider social media platforms handling user interactions daily. Feeding posts to users' feeds requires efficiently retrieving relevant content without overwhelming servers. Efficient algorithms ensure quick load times while maintaining high throughput capabilities. A naive approach might check every post against every user preference, resulting in O, n superscript 2 complexity. However, optimized systems employ indexing techniques reducing complexity closer to O, n log n. Search engines face similar challenges in delivering fast results despite enormous datasets. Their sophisticated ranking algorithms must balance speed with accuracy requirements. Even basic tasks like file compression rely heavily on algorithmic optimizations. Lossless compression methods need precise control over bit manipulation processes. Each of these scenarios demonstrates the importance of considering time complexity during software development cycles. Properly analyzed algorithms contribute significantly towards creating scalable, maintainable applications. Differentiating between best, average, and worst-case scenarios when analyzing algorithms, it's essential to distinguish between various scenarios they might encounter. Understanding these distinctions helps create more accurate performance expectations. The best case represents ideal conditions where the algorithm executes optimally. For sorted arrays, binary search achieves O, log n, time complexity in the best case. The average case considers typical situations encountered during normal operation. Most sorting algorithms have average case complexities equal to their worst case scenarios. The worst case describes the most challenging input configurations that could potentially slow down an algorithm significantly. Quicksort's worst case degenerates to O, n superscript 2 when dealing with already sorted lists. Recognizing these scenarios enables developers to choose appropriate algorithms for particular use cases. Some applications prioritize worst-case guarantees over average performance improvements. Security-critical systems often require strict worst-case bounds to prevent denial-of-service attacks through malicious input patterns. Measuring space complexity while time complexity receives significant attention, space complexity is equally important in algorithm evaluation. It measures the extra memory used by an algorithm beyond its input storage. Evaluating space usage helps optimize memory consumption, especially in constrained environments like embedded devices or mobile applications. Simple algorithms often exhibit low space complexity. For example, iterating through an array consumes minimal additional memory compared to recursive solutions. Recursive functions introduce overhead due to function call stacks. Each recursion level adds new frames onto the stack, increasing overall memory footprint. Data structure selections greatly influence space requirements. Using linked lists instead of arrays changes memory allocation strategies entirely. Choosing between in-place versus non-in-place modifications affects temporary memory needs considerably. Many sorting algorithms offer both variants depending on implementation preferences. Comparing different sorting algorithms serve as excellent subjects for comparative analysis due to their diverse complexity profiles. Let's explore several popular options and their respective performances. Bubble sort operates by repeatedly swapping adjacent elements if they're in wrong order. Its simplicity comes at the cost of poor efficiency, with O, n superscript 2, time complexity in all scenarios except trivial ones. Insertion sort builds up a sorted list incrementally by inserting each new element into its correct position. While still having O, n superscript 2, time complexity, it performs reasonably well on nearly sorted datasets. Merge sort divides the dataset recursively into smaller subsets before merging them back together. This divide-and-conquer strategy yields O, n log n, time complexity consistently across all input types. Quicksort selects a pivot element and partitions the array around it. Although it averages O, n log n, performance, its worst-case time complexity degrades to O, n superscript 2. Heap sort constructs a heap data structure then repeatedly extracts maximum elements. Like merge sort, it maintains stable O, n log n, performance regardless of input configuration. Selecting the optimal sorting technique depends largely upon specific use cases and constraints. For instance, heap sort might be preferred when worst-case guarantees matter most. Advanced concepts in algorithm analysis. As we delve deeper into algorithm analysis, we uncover more nuanced concepts that refine our understanding of computational efficiency. Lambda calculus provides foundational principles underlying functional programming languages. It influences how we model computations mathematically within algorithmic frameworks. Turing machines represent theoretical models of computation capable of solving any computable problem given sufficient resources. They help establish fundamental limits on what computers can achieve. P versus NP theory explores whether certain problems inherently resist polynomial time solutions. This ongoing research area shapes modern cryptography practices significantly. Amortized analysis evaluates average costs over sequences of operations rather than individual steps. Techniques like accounting method and potential method facilitate this assessment effectively. Probabilistic analysis incorporates randomness into algorithm evaluations. Randomized algorithms utilize probability distributions strategically to enhance performance characteristics. These advanced topics expand our analytical toolkit beyond simple time-space complexity metrics toward broader computational paradigms. Common pitfalls in algorithm analysis. Despite its importance, algorithm analysis presents several pitfalls that developers must avoid to ensure accurate assessments. One common mistake occurs when overlooking hidden constants behind big O notations. 2O, n. Algorithms might differ substantially in real execution times due to varying coefficients. Overlooking practical considerations can lead to suboptimal implementations. Sometimes, an algorithm with higher theoretical complexity proves faster in practice due to cache-friendly memory access patterns. Failing to account for hardware specifics hampers meaningful comparisons between algorithms. Memory hierarchy effects often dictate actual performance outcomes differently than predicted purely by complexity analyses. Ignoring problem-specific properties might result in unnecessarily complex solutions. Tailoring algorithms to exploit domain knowledge frequently enhances real-world effectiveness. Carefully balancing theoretical analysis with empirical validation ensures robust decision-making regarding algorithm choices in production settings. Tools and resources for algorithm analysis. Variety of tools exist to assist developers in conducting thorough algorithm analyses. Profiling tools help measure actual runtimes while complexity analyzers verify theoretical predictions. Popular profiling utilities like Prof and Visual VM enable detailed examination of program behavior, including CPU usage breakdowns and memory consumption patterns. Online platforms such as LeetCode and HackerRank offer interactive coding exercises, specifically designed to reinforce algorithmic concepts practically. Academic literature provides rigorous mathematical treatments covering formal proofs related to algorithm correctness and efficiency claims. Community forums like Stack Overflow and Reddit host discussions where professionals share experiences regarding algorithm optimization challenges faced in industry settings. Combining these resources creates a holistic approach enabling comprehensive understanding of algorithm behaviors across theoretical foundations and real-world applications alike. Conclusion: effective algorithm analysis forms the foundation of building performant software solutions. By understanding time and space complexities, developers gain critical insights necessary for making informed technical decisions. Mastering these analytical skills empowers programmers to select optimal algorithms tailored precisely to their project requirements. Whether developing web applications or high-performance computing systems, sound algorithmic judgment remains indispensable.